So starting from this class, we're going to talk about other air pollutants. Okay, so that's going to be the focus of our second half of the semester. So basically, in our first class, we introduced that there are just so many types of the criteria air pollutants, right? 6 of them. And we have been focusing on PM, right? And so from this class, we're going to talk about the sulfur dioxide, which is also one of the criteria air pollutants. Originally, I mean, for the previous semesters, when I teach the air pollution class, typically the sulfur dioxide is at the end of the semester. And I got quite some complaints from the students regarding the team project, because as you see, in your team project, you need to design a PM removal device and a sulfur dioxide removal device, right? So at that time, some of them complained that mainly it's at the end of the semester where you have to work on the project and also the final. So you guys probably won't have enough time. So that's why this semester I decided to move the sulfur dioxide earlier to the semester. So theoretically, after this chapter, you should be able to come up with everything you need regarding the team project. And if you haven't get in contact with your team members yet, please do so quickly. So this year we have more members. Basically, I think it's 8 students each team, right? So you'll have more, basically more team members to work with you on this project. And try to get this early so that you don't pack everything at the end of the semester, okay? So of course, the sulfur dioxide control will not be a part of the midterm exam, but still pay attention to these concepts, because after the midterm, we're going to come back to the sulfur dioxide and then discuss more information on the control devices, okay? So before we introduce new contents, we still have one thing left. I just graded your, I think it's homework 7, that's the latest homework on the backhouse filters. So I did mention that, I did notice that there are a few misconceptions regarding the solution of these problems. Maybe because in the class I went through the content so quickly. So I saw that quite many of you still have some misconceptions regarding the design of the backhouse filters. So I think it's probably necessary for us to go through this in more details, right? So this is what the problem states in your homework problems. So it wants us to estimate the net cloth area for a shaker backhouse, right? And then it wants us to filter the polluted gas or the flue gas at a flow rate of 70,000 CFM, that's cubic feet per minute, right? And then it has certain concentration of the particles, and it specifically mentioned that this is flour dust, okay? And also, so basically, it wants us to specify the number of compartments we need for this backhouse filter system, and also calculate what is the total number of the bags. So if we are provided with the geometry of each filter bag, so the filter bag is 6 feet long and 6 inches in diameter. So what that means is, basically, it wants us to design several compartments of the backhouse filter, right? And then in each compartment, we need to come up with how many filter bags we need, right? So this is what this question is asking us about.
Dr. Wang,
so,
I cannot see your screen.
You cannot see my screen? Let me see. Do others have the same problem here?
No, I can see.
I can see it.
Okay. Yeah, so Doa, you might want to check your video there.
Okay. I can see your picture now, just. I cannot see.
You cannot see my screen?
Yes, no, just I see your picture, just.
Oh, just my picture, okay. So can you try to quit the meeting and then rejoin again? And then just let me know if that works. So do others have the question other than Doa on the screen? Okay, I think we can continue. So Doa, if you have question in seeing this, if you miss this short section, you can go through our video after the class, right? This is also being recorded. So basically come back to this question. It wants us to come up with a detailed design for this shaker backhouse. And in the class, we mentioned that for these design problems, we need to go through several steps. And I basically listed these steps here. And I recommend you to go through this step one by one so that it's more clear in terms of the design. All right. So basically, the problem provides us with some conditions. It gives us the total flow rate, right? And the type of the particle, or the type of the PM, right? It also gives us the height and diameter of the filter bag. So it wants us to come up with the entire system design. Right? So basically, if we follow this sequence here, the first step we need to take is refer to this table 6.1 to find the maximum filtering velocity for this type of PM. Right? We notice that this is flour dust, right? So what we do is we go to this table here and then find where the flour dust is located. And I think we also had a quiz during our class and we introduced this concept here. Basically the flour is here, right? So you can find that the maximum filtering velocity is going to be 2.5 feet per minute, right? So we can find basically step one, V is 2.5 feet per minute. Okay. So with this information, we can calculate what is the required area of our backhouse filter system, right? Because it's already provided with us the flow rate. So basically the flow rate divided by the filtering velocity will be the area or the entire area of the backhouse filter. Right? So for this problem, if we plug in the values, 70,000 divided by 2.5, and since they are in the same set of units, we don't need to convert any unit to the standard unit, right? And then we can find out that this is 28,000 square feet, right? So I saw that some of you actually just stopped at here and was just using this number as the basically the total area of the backhouse filter. But basically what this number gives us is the minimum required area, right? It cannot be this area in real application because the actual area of the backhouse really is determined by how many backhouse filters we put in the system, right? We need to use that number and then multiply the area of the filter to get the total area. So this is just the minimum required. So this is not the final answer yet, all right? So that's why we have to go through the next step. So basically the third step is going to be refer to this table 6.3 to choose the number of compartments, which is a capital N here, right? So since we have the total area, 28,000 square feet, we'll come to this table 6.3, and then we can find that the number of compartment is going to be 6 or 7, all right? So I saw that some of you chose 6, some of you chose 7, and we can actually go through these options one by one, okay? So first, let's say that we decide that the number of compartments is 6, right? So now, once we get to this step, we need to come up with a detailed design of each compartment. So what this tells us is that now we're decided that we're going to build 6 of compartments. 1, 2, 3, 4, 5, 6, right? The problem wants us to calculate what is the number of compartments, and we have already got this. That's going to be 6. It wants us to also calculate the number of bags that's required for each compartment. So that's why we have to further go into the detailed design of the compartment. So quite many of you got 2 points deducted for this problem, mainly because you guys didn't further go into the details here, right? So once we have this total number of compartments, we mentioned that the first step is to calculate what is the area of the filter in each compartment. And that is calculated by AC equal to A divided by N minus 1, right? The reason why we put this -1 here, is to consider the cleaning of the compartment, right? So we mentioned that for these shaker backhouse or for the reverse air backhouse, periodically we need to remove the whole compartment offline, right? So this is going to be offline. And what the remaining backhouse does is basically 5 of them will be running at a higher velocity, filtering velocity, to filter out the particles, right? We cannot just design 6 compartments exactly. Well, if we remove one, and then that's going to cause some like higher pressure, right? Or a higher velocity there. So what this means is that we have to make sure that the remaining 5 backhouse can still provide the same or the minimum area that's required for this entire system, right? So what this means is that we need to put in 28,000, and that's divide that by 6 minus 1, right? So basically this means that the remaining 5 backhouse compartments can still provide the minimum area for this design area, right? So by using this equation, we can find out that the area of the filters for each compartment, that's 5,600 square feet, right? So with this detailed design of the compartment, now we can come up with the question on how many filter bags we need for each compartment, right? So this is the total area that's required by the compartment. And now we just need to calculate what is the area of each filter bag. So that is calculated by, let's say each filter is pi multiplied by d multiplied by h, right? So that's 3.14 multiplied by d, that's the diameter of this filter bag, which is 0.5 feet, right? 6 inches is 0.5 feet. And then we multiply that by 6 feet. So this is the area of the of each filter bag, and that turns out to be 9.4 square feet. Right. This is the area for each filter bag, and then to calculate how many filter bags we need for this compartment, we just need to divide AC by AF. Right. So this is the area. This is the number of the filter bags we need for each compartment. So if we plug in the values, 5,600 divided by 9.4. So we can get basically 595 filter bags, right? And this is the number of filter bags we need for this compartment here. And as I mentioned a lot in our last class, we shouldn't stop here, because in terms of the design for the filter bag, we need to also design how many rows and how many columns we need for each compartment, right? Because finally, these filter bags are arranged in these rows and columns. And the number we need for each compartment must be a practical number. It cannot be a single line of the filter bags, or let's say just 2 rows of the filter bags, well, a long column, very long column for the filter bags, right? So it shouldn't stop here. We need to come up with a design of how many rows and how many columns we need, right? And then 955 isn't really a good number for us to design the rows and columns. So what you can do is you can round it up to 600, okay? we're not affecting the total number of filter bags significantly, but just by adding 5 more, we can come up with a design of 20 multiplied by 30, right? So this is a design for each compartment. And this is basically the final step we need to get into, right? And everything else is just using this design to back calculate how many filter bags we need and what is the total area of the cloth, right? So if we know that we need 600 filter bags for each compartment, and then to calculate what is the total number of bags, right? It asks us total number of bags, then we just need to use, let's say, so this is the practical design. This is a 6-step practical design of the compartment. We decided that should be 20 multiplied by 30. And then in our 7th step is to calculate the actual area or actual number of the filter bags and the filter area, right? So the actual number, let's say NA, is going to be equal to the number of compartments multiplied by the number of filter bags in each compartment. So that's going to be 6 multiplied by 600, 3,600 filter bags, right? And then the actual area also depends on how many filter bags we use in the actual situation, right? So that's going to be AF, which is the area of each filter bag, and then multiply that with NA, which is the total number of the filter bags. So that's going to be 9.4 multiplied by 3,600, and you can get 33900. Okay. So this is how we calculate the actual area of the filter bags and actual area of the or actual number of the filter bags in the system. Okay. So everything is determined by this 6th step, which is the practical design of the system, right? We cannot just stop here. We need to come up with a more realistic or more practical design for the system. Right? So I noticed that some of you also chose the number of 7 here instead of 6, right? So if it's for 7 compartments, what we need to do is to change this n number to 7, right? And then I'll just write out the answer here. So basically in the 4th step, what you have is AC is equal to 4667 square foot. And the 5th step, N is equal to 495. Basically 495.4, okay? So similarly, we should make this number more realistic. So we should first round it up to 496, right? It might be a little bit difficult to come up with the rows and columns. So why don't we just change it to 500, right? So if it's 500, then that should be 20 multiplied by 25. Basically 20 rows, 25 columns, right? So this is practical design for each compartment, right? So with this number here, so basically with this number here, this is the practical design. With this number, we can calculate what is the actual number of the filter bags in the filter area, right? So in the 7th step, NA, or the actual number of the filter bags is just N multiplied by N. We need 7 compartments. Each compartment, we need 500 filter bags. So that's 3,500 filter bags, right? And in terms of the filter area, that's just AF multiplied by NA, right? 9.4 multiplied by 3,500, that's 35970. Okay, so this is how we design the backhouse filter system. So what I want to mention is that to solve this problem, we shouldn't just stop here because this is the minimum required area. It's not the actual area of the backhouse filter system, right? And then also once we come up with the number of compartments, when we calculate the area of the filter bag in each compartment, we have to divide this total area by n-1. This is to consider the cleaning condition where we remove one of the compartment offline. So basically what that means is that the remaining compartments have to have the minimum area of the filter bag, right? So that's where we divide this 28,000 by 6 minus 1. So in that way, we make sure that when we multiply the AC by 5, which is the remaining number of compartments, the total area still can satisfy this requirement, right? And then once we have that, so basically there are several things that I want to mention, right? So this is the important thing. This is not the final answer, right? This is an important point. We need to consider the cleaning of the compartment, which is taken offline, right? And this is another important point, which is a practical design of the compartment, right? We shouldn't just use this number here because it's quite difficult to arrange an irregular shape of the compartment. So once we have this practical design, we can back calculate what is the total area of the filter bag and what is the total number of the filter bags. Okay. So I hope this process make it more clearer in terms of the backhouse filter design. So if you still have questions, do let me know. This is a quite important aspect in terms of the PM control device.
Yes.
Yeah.
I have a question, please.
What's it?
I have a question.
Yes.
Yeah, about the same question, I choose n equals 7. So I round up 495 to 496.
Mm-hmm.
Then I put the number of rows 16 and columns 31. It's okay?
That's okay. That's okay. As long as you don't get something like 2 multiplied by 200 something. That's fine. Yeah.
Okay, thank you. Just yeah.
Mm-hmm. Yeah, it's just sometimes it might take time to do this calculation here, right? And of course, this will save some cost in terms of how many filter bags you need. But I think in terms of the design problem, we may prefer to just use a more simplified number here, right? 20 by 25. So as long as you don't have a very large aspect ratio in terms of the columns and the rows there, that should be fine. Okay. Any other questions? So if not, let's just go to the new contents here, right? So we're going to spend some time regarding the sulfur dioxide control. So we mentioned that sulfur dioxide is one of the criteria air pollutant, which is basically one of the most important air pollutants we carry in the atmosphere, right? So we mentioned that the major issue for that is sulfur dioxide can cause respiratory system. It's basically bad for human health. So once we inhale that, it's going to cause some allergy or cause some cell damage there. So also based on the definition of the air pollutant, it's not the species, not only the species that harms the human health. They should also include the species that's causing damage to the human society, right? For example, the constructions or properties or livestock, so on. So that's why sulfur dioxide is also bad in terms of that way, right? Because sulfur dioxide can form the acid rain, okay? So here I'm showing 2 pictures of a very famous construction here. So just as a part of the quiz, so could you let me know where is this construction here? We know that this is called Taj Mahal. A very simple quiz question. All right, 10 more seconds. just stop here. All right, everyone get the correct answer. And I think there are 3 that who didn't, probably didn't have enough time to search on Google, I guess. So it is indeed in India, all right? There are some history associated with this construction as well. But nowadays, let's say if we look at the construction here, a lot of time you can see is that the surface of the construction becomes quite yellow. Right? It is not because of the sunrise or sunset. Right? So actually people there periodically clean this outer surface of the construction, right? Because we know that this construction is made of limestone. So limestone is mainly calcium carbonate, right? And once we form the acidic species, for example, acid rain, they're going to corrode the surface of the construction, right? So what happens for this acid rain formation is basically sulfur dioxide get emitted into the atmosphere and they can react with water, right? We can first form sulfurous acid, sulfurous acid. Okay, sulfurous, this should be 3 here. And then further, the sulfurous acid will get oxidized by the oxygen in the air, and then form the sulfuric acid. So we know that the sulfuric acid is a strong acid in all the families of acids, right? And then simply, let's say for the raindrops, typically the raindrops will have a pH of around 5.5, right? We know that pH 7 means neutral, right? pH of 5.5, that means it's already acidic, right? So the reason for the raindrop to be acidic under normal conditions is not because of the sulfur dioxide, it's actually because of the carbon dioxide. So carbon dioxide can get dissolved in water and then form carbonic acid, right? So carbonic acids are also acidic, and this is going to change the raindrop to a kind of a weak acid. But when there is sulfuric acid, or when we form acid rain, the pH can further drop to around 4, okay, which is very acidic, right? And because of that, the sulfuric acid can react with limestone and then basically corrode the surface, right? So what happens is sulfuric acid can react with calcium carbonate and then form calcium sulfate plus water and carbon dioxide, right? So basically it's going to corrode the surface of the construction here, right? So that's why the acid rain or the sulfur dioxide needs to be controlled. Otherwise, a lot of the famous constructions will be damaged, right? So not only the acid rain damages the constructions, it also harms the life of the ecosystem, right? So here again, I'm showing a picture of the Smoky Mountain, the Great Smoky Mountain. So we mentioned that the smoky or the hazy environment is not because people camping there. It's actually because of the secondary formation of the particles, right? Mainly because there are a lot of VOCs being formed by the plants, and then let's say some industrial emissions from the cities nearby, they can react with these volatile organic compounds and then form the PM. But when you go to these higher mountains, I think this is a picture that's taken at the Clemens Dome. So next time, if you have the chance to go to the Smoky Mountain, and this is a very famous scenery point in the Smoky Mountain. So if you look down there, you see a lot of forests are getting damaged there, okay? And this is actually because of the acid rain. The acid rain can corrode the leaves and then basically harm the lives of these plants. So we also like to see the fall foliage, right? We want to see the foliage color, letting them turning orange or turning red. When we go to the forest, we definitely don't want these things to happen. You can see that actually the sulfur dioxide is causing a huge damage to our entire society. But in terms of the emission of the sulfur dioxide, we're actually doing a pretty good job, right? So here it's showing the sulfur dioxide emissions in the United States from 1970s to 2017. Okay, so this is in 1,000 tons. You can see that there is almost an exponential decrease of the sulfur dioxide. And again, this curve starts from the year of 1970. Okay, what happened in this year? It's the EPA, right? We mentioned that the EPA was established in 1970. And so basically, starting from that point, people start to realize that sulfur dioxide is causing some trouble to our environment. And then we have a more stringent control, or we design the environmental engineering devices to control or to capture these sulfur dioxide. So how did we achieve this goal? How did we do it? We must come up with, be associated with some sulfur dioxide control devices, right? But before we talk about how do we do it, we need to know what is the major source of the sulfur dioxide. So here I have another quiz question. So let's just take a look. So what is the major source of the sulfur dioxide? Right here I'm listing 3 potential sources. And if you consider the major source, what might it be? So I think I'm hearing some background noise here. Can you guys hear that too? It's a microwave turning on or something. All right, so we'll just stop here. Let's share the results. Yeah, actually, most of you get the correct answer. So coal-fired power plant is a major source of the sulfur dioxide. So I'm also listing a few more, like vehicles or cooking. So actually, later you can find out why vehicles is not a major source of sulfur dioxide, mainly because the oil refineries, they already took care of this problem before the gasolines are delivered to the vehicles. Okay, cooking is definitely not a major source, because when we cook, let's say vegetables or meat, there are not a lot of sulfur in there, right? And so that's why coal-fired power plant is a very important one. So as a matter of fact, if we break down all the sulfur dioxide emission, so 2/3 of them are actually coming from the coal-fired power plant. All right, and the remaining 1/3 are coming out of the oil refinery. So basically, the oil refinery changes the crude oil into the products we need. For example, the gasoline. So the oil refinery will deal with the sulfur, and that's why the product we receive don't have much sulfur anymore, right? And so now let's just look at how these 2 devices, or how these 2 sources deal with the sulfur dioxide, right? So first, so basically these 2 devices, they deal with the sulfur dioxide in 2 different ways. So there are 2 methods to control the sulfur dioxide. One is before the combustion. One is just before we burn any fuel. we will deal with we will purify the fuel there. So this method is called the fuel desulfurization, right? We just deal with the sulfur that's in the fuel before we combust them. And the other method is basically after combustion. That is called the flue gas desulfurization. You can see that basically this deal with the flue gas, which is already the product coming out of the combustion of the fuel, right? And the oil refinery uses the fuel desulfurization, basically to clean or purify the crude oil, remove the sulfur, and then deliver to the customers. And the coal-fired power plant deal with the sulfur dioxide after we burn the coal from the system, right? So first we'll talk about the oil refinery system, which is using the fuel desulfurization. So as a matter of fact, when we talk about the crude oil, the sulfur is basically the highest or the most dominant element after carbon, hydrogen, and oxygen. So the sulfur content in the crude oil is very high, so right after the carbon, hydrogen, and oxygen. So typically, these sulfur are existing as a structure of R, which is an organic component that has a single bond with the sulfur, right? So whenever we burn this oil or the crude oil, the sulfur will just get released into sulfur dioxide and then get released to the atmosphere. So as a matter of fact, people have their own names to describe the crude oil that has different contents of the sulfur. So let's say if the sulfur content is higher than 0.5%, then we'll call this crude oil, as the sour crude. Okay, this kind of makes sense because if we burn the oil here, we're going to get sulfur dioxide and then further get sulfuric acid, right? So that's why it's going to be sour here. And if the sulfur is below 0.5%, we actually call it sweet crude. Okay. And of course, people would like to deal with this sweet crude because we're not generate much pollution out of it. But as a matter of fact, 80% of the world crude oil are sour. Okay. So we have to deal with the sulfur coming out of this system. So you might have the question, why can't we just deal with this crude oil similar to the coal-fired power plant method? So why can't we just deal with it after we combust the oil or combust the gasoline? But if you think more carefully, let's say if we try to deal with the sulfur dioxide control by the customers, right, after the combustion, what that means is we have to add devices to our engine emission systems, right? We already know that we need to do engine check pretty much every year or every 2 years, right? That's already quite complicated enough. And if there are some glitches or some problems with the emission control, then we might be emitting a lot of sulfur dioxide into our neighborhood. And then that might cause some health issues to the people, right? And further cause some more complexities there. So that's why the oil refinery prefer to deal with the sulfur before the products are delivered to the customers. Okay, so the method they use is actually by introducing hydrogen to the sulfur-containing crude oil. So what happens is under certain high temperature and pressure, we can introduce hydrogen. Hydrogen are going to react with the sulfur-containing crude oil to form R and hydrogen sulfide. Okay, so hydrogen sulfide, unfortunately, this is also a pollution gas. It's also toxic. Okay, it's also toxic to humans. So we basically convert the sulfur into a hazardous or pollutant from this reaction here. But at least this step ensures that the product we deliver to the customer or the oil refinery delivered to the customer is clean. Okay, so they don't need to worry about the sulfur coming out of their vehicles. Okay, so guess what happens to these hydrogen sulfide before the year 1970s? Okay, so basically before the year 1970s, all these oil refineries, they can form hydrogen sulfide from their reactions there. So what they did at that time is just to combust the sulfur dioxide, the hydrogen sulfide. Okay, they just burn this extra gas, and this is not a solution to an environmental engineering problem. This is not stopping the pollution. This is just a redistribution of the pollution. Okay, because the product coming out of this reaction is still sulfur dioxide and water. Okay, so we're not dealing with the sulfur dioxide at the customers, but we're directly generating the sulfur dioxide at the oil refinery, and this is not a solution to this environmental problem. And because of the EPA, after the year 1970, people have to be more imaginative to this hydrogen sulfide problem. Okay, so if you further look at the hydrogen sulfide, and then basically we're trying to control the emission of the sulfur dioxide, right? So if you look at these two pollutants here, we can come up with a better solution there, right? We know that the hydrogen and oxygen, they can combine together to form water. The water is not a pollutant, okay? So why can't we just combine the sulfur here to form sulfur solid? So this is a reaction that people discovered, right? And then the final product that's coming out of this reaction is just solid sulfur and water here. So if you want to balance this equation, we need two numbers of the hydrogen sulfide so that we can form two numbers of water molecules here. And then for the sulfur, we'll get 3. Okay. And the sulfur is a very important commodity. Okay. It has very wide applications. For example, the gunpowder. Okay. Fireworks. That's why, let's say during the July 4th, after the fireworks stops or finishes, you can smell those sour type of smell, right? And those are the sulfur dioxide coming out of the fireworks. Sorry about that. So basically, people can also use that to form some more purified chemicals. So they can use that sulfur to form very clean or very purified sulfuric acid, right? And then we can also use this sulfur in paper bleaching. Okay, so the solid sulfur has very wide applications. And now if you look at this equation here, we're basically solving two problems with one equation. This is a typical 2 birds, 1 stone solution. And you can see how environmental engineers come up with this almost perfect solution to this problem. So it turns out that this process, people also call that as the Claus process. Okay, so it turns out that this process coming out of the oil refinery, it can provide almost 90% of the supply of the sulfur in the US. Okay, just the this reaction here coming out of the oil refinery, they can provide 90% of the sulfur supply in the US. Of course, it's generating more, and then the US is also exporting the sulfur to all the different countries. Okay. So you can see that this is a very powerful process for us to deal with the sulfur dioxide coming out of the oil there, right? So next time when you go to see the fireworks, when you smell the sulfur dioxide, you can think of this process. It's coming out of the oil refinery. This is a very effective solution. Okay. So this is the fuel desulfurization. You can see that basically this method can deal with the sulfur in the crude oil, right? And then you may wonder, so why can't we use the same method or the fuel desulfurization for coal-fired power plant? So why can't we use this method for coal, which are basically solid black particles that we get or dig out of the mine? There are certainly difficulties with this method because here, when we're talking about the reaction is taking place in the liquid form or in the gaseous form, right? So we know that the reaction taking place in these forms, they can complete more, they can be reacted more completely, right? Basically, we can either bubble the liquid or just vaporize the crude oil, right? To let the reaction complete more faster or more completely. But if we're talking about the coal particles, which are solid, that's going to be more challenging because let's say if we want to introduce hydrogen into a coal particle, then there's always sulfur distributed almost uniformly everywhere in this coal particle, right? And then it's going to be very ineffective if we're trying to deal with the sulfur that's at the core of the coal particle. So that's why for this method, or the fuel desulfurization, it cannot be easily applied to solid forms of the fossil fuels, right? We cannot use the method for the coal particles, and they're being more widely used in the oil refinery for crude oils. All right. So for this flue gas desulfurization, people also call them as the FGD for short. So here is a map of the coal-fired power plants that's in the United States until 2010. Okay, so this is also labeling how many of them are using the FGD system to control the sulfur dioxide, how many of them are planning for the FGD, and how many are basically there's no FGD. Okay, so you can see that at that time, or at least 2010, maybe around 50% of the coal-fired power plants already are equipped with FGD, or they have planned for the FGD. Okay, so there's pretty much still a long way to go for a lot of other coal-fired power plants, right? But I would say that for the newer power plants, typically they are incorporated with this FGD system because EPA is putting a more stringent requirement regarding the sulfur dioxide emission. So we're not saying that all of these power plants that don't have the FGD are emitting a lot of sulfur dioxide because it really depends on how many sulfur are there in the coal sources, right? In the coal that they are combusting. For example, if the coal that they're using are very clean, that doesn't have any sulfur there, or the sulfur content is very low, they don't necessarily need the FGD. It's just when they're burning coals that have more sulfur in there, they need to consider incorporating the FGD system, okay? And in terms of the flue gas desulfurization system, there are multiple methods here. So we can use limestone scrubbing, we can use the lime scrubbing, lime spray drying, and trona injection. So I think for your project design, we're talking about either trona injection or lime injection. All right, so we can talk about more details of this FGD systems in our future classes. Okay, so again, a reminder for the schedule for this week. So on Wednesday, we're going to have the exam. So again, I want to mention that we need to turn on the web camera. You can either use your computer or use your cell phone or tablet. Okay, so I need to see your workspace. If you have technical difficulties, just let me know. I can arrange a testing center for you, right? So on Wednesday, we don't have classes, and then we're going to continue the sulfur dioxide control next week, all right? So that's all for this class. Let me know if you have any questions, all right?